There are two kinds of people in this world: those who are comfortable with numbers and those who are sheep. Numbers describe every aspect of reality. Numbers can characterize and quantify the physical world. They're used to manage the food you eat, the job at which you toil, and the quality of your life. There are numbers that define reasonable human health. Stray outside those numbers and you may be taking your life in your hands. The Black-Scholes formula is used to price financial derivatives, which affect the health of the economy in which you live. In North America, your financial soundness is summarized by a FICO score that quantifies a borrower's loan default risk and heavily influences whether you can get a loan and the interest rate you'll be charged. Your SAT scores could determine the college you go to. Statistics is integral to every scientific, economic, medical, environmental, political, and financial endeavor. The universal constant, small c, is the upper limit at which light or matter can travel through physical space. Another number, big G, describes the universal gravitational constant that we use to predict the motions of objects through near space with exquisite precision. Numbers can be used to study the past, to manage the present, and to predict the future. If you're numerate, if you know how to read a graph to recognize a trend, if you can visualize geometric relationships, in short, if you understand how to enhance your knowledge of the world by working with the numbers that describe it, you have in your grasp a certain amount of control and a degree of awareness that others don't have. To grok the world, you must grok numbers. On the other hand, if you're innumerate, then everything is a mystery and an unpleasant surprise. Why were you charged a higher rate on a loan than your neighbor? Why doesn't that one crucial traffic light on your morning commute ever work to your advantage? How much more money do you need for retirement? And why don't you go flying off the face of the earth if it spins at over 1,600 kilometers per hour at the equator? If you're not comfortable with numbers, then Dell pouring water on a football will be an utterly convincing proof that gravity doesn't exist. P-Brain's assertion that the earth can't rotate because we'd all be flung off its surface makes complete sense, and the Globebuster's assertion that electromagnetism can replace gravity will seem perfectly obvious. It's no surprise they don't provide a mathematical treatment of their assertions. They're innumerate, so they can't, and if they got someone to do the calculations for them, the results would contradict their narrative. What follows is a strong falsification of the flat Earth hypothesis. It brings together a key observation about how the northern pole star, Polaris, is seen from Earth, along with refutations of the most commonly proposed mechanisms for replicating these observations on a flat Earth. It relies on the geometric relationship between a distant light and an observer on the Earth. How can you tell if segment AB is parallel to segment CD? Lines are parallel if they don't share any points, but these are line segments, so they don't extend into infinity. Assuming only two dimensions, one way to answer the question is to measure the distance from 2 points on segment AB to the points on CD that are perpendicular to them. If the distances are the same, the segments are parallel. This is an example of how you can evaluate a property of one object by reference to another object. Now say AB is an arc. CD is still a segment. Let's call the point on AB closest to CD nearest point, or NP. Divide the arc into smaller sections of equal length, starting from the nearest point, and call them locators. Each locator has a twin on the other side of the nearest point. Twins are equidistant from the nearest point. Also, each locator has one point on CD that it's nearest to, which is the point at which a perpendicular line from any point on CD intersects AB. Its twin also has such a point on CD, and the distances from the twins to their nearest points on CD are equivalent. If you don't actually know the shape of AB, then by measuring the distance from each locator to CD and plotting the results, you'll approximate its shape. Things get complicated if AB and CD are very far away from each other, and your measurements of distance aren't that precise. If your precision is less than the change in distance from one locator to the next, your measurements will be unreliable. Measurements of distance from adjacent locators will have insufficient precision to be reliable. You can address this precision problem by using angles instead, because angles don't depend on distance. The angle above eye level at which an object is located is its declination. The pattern of declinations measured at increasing distance from the nearest point will determine the shape of AB, because each geometric shape has a distinctive pattern of declinations to a distant external reference point. I wonder what this one could be. Now, imagine you find yourself on the featureless surface of a large object. The object is so large that you can't discern its shape just by looking. Let's apply what we've just learned to our situation. We can trace its surface with respect to an external reference point. In the real world, if the reference point is at optical infinity, you can measure its declination from various locations on the surface of your home object and determine its shape. Each shape will have a set of declinations associated with it. If all the measurements are the same, then you're standing on a flat surface. You can't tell if this is an endless flat plane or a disk, or the flat end of a cylinder, or one face of a cube, or some even more exotic polyhedron. If the measurements are the same up to a certain point, then change abruptly to a different consistent value, you may have encountered a vertex between two planes. And if the declination varies consistently with the distance you travel, you may be on a sphere. In order to get these measurements, you need a fixed reference point from which to measure the visual angle. It has to be far enough away that the light coming from it is parallel to you, at optical infinity, in other words. Let's see if we can learn something about the Earth's shape in this way. In the constellation of Ursa Minor is a triple star system designated Alpha Ursae Minoris, but commonly known as Polaris. Polaris AA, a yellow supergiant with an apparent magnitude of 1.98, is the star we see as the North Star. It has a small companion, Polaris AB, with an apparent magnitude of 9.2 that orbits the main star at about twice the distance that Saturn is from the Sun. This pair is in orbit with Polaris B, which has an apparent magnitude of 8.7 and orbits the other two at a distance about 60 times further from the pair than Pluto is from the Sun. Polaris is located nearly directly above the Earth's northern axial pole at optical infinity. The key point is that the declination at which an observer sees Polaris always changes at a linear rate with the observer's northern latitude. Another aspect of this geometrical relationship between the observer's position on the Earth and the declination of Polaris is that the latter is generally equivalent to the observer's northern latitude. The only geometric figure for which this observation is possible is a circle, which corresponds to a line of longitude on the Earth. Since this observation is true for any longitude north of the equator, it also applies in 3 dimensions to, and only to, a sphere. The Earth must therefore be a sphere. To be clear, this real-world observation is geometrically impossible on a flat plane and thus falsifies the flat Earth. We'll see why shortly. To salvage their shared fantasy, flat earthers have resorted to several justifications, none of which succeed. Let's begin with a scenario with the least support in the flat Earth community, a distant Polaris. The biblical literalist faction claims there's a dome over the flat disk of the Earth, so nothing can be too far outside that dome, if at all. But for the sake of completeness, let's cover this. In this scenario, Polaris at optical infinity on a flat Earth results in a set of 90-degree declinations regardless of your location on Earth, as shown by the red line in the graph. This clearly doesn't match reality, except at the North Pole. The first attack on this observation with any kind of support in the flat Earth community attempts to cast doubt on the distance of Polaris from Earth. The claim is that the star is actually a small light, perhaps on the dome, perhaps within its bounds. It's hard to say because presenting a model for scrutiny invites falsification, so flat earthers are notoriously coy about offering one. Regardless, we can assume flat earthers believe the light is not much further than the dome, since a large universe is explicitly ruled out by nearly all globe deniers. The issue with any flat Earth model is that the distance to the light depends on the observer's latitude. In this scenario, we assume that the measured declinations are accurate, then determine Polaris's altitude based on those observations. A basic application of trigonometry shows that as the observer's distance from the North Pole increases, the altitude of Polaris must decrease in order to maintain the viewing angle observed in reality. Two observers at differing latitudes would thus see Polaris at different altitudes simultaneously. Barring some mystical ad hoc explanation that engenders more questions than it answers, this is a problem. Clearly, a nearby Polaris presents insurmountable problems for globe deniers. What positive evidence do we have that Polaris is far away? Polaris is between 323 and 433 light-years from Earth. The uncertainty arises from the different methods used to measure that distance. Spectral analysis yields the lower value, while stellar parallax measurements by the Hipparcos and Gaia astrometry satellites support a higher number. That being said, the primary point is that various unrelated methods result in distances in the hundreds of light years, easily putting Polaris at optical infinity. Light rays from the star arrive at Earth effectively parallel to one another. This will become important later. So how do we measure stellar distances? Stellar parallax is the apparent shift in the position of a nearer star against a more distant background. The angular change due to parallax is an input to a simple equation to determine the distance to that star. Assume for the moment that the star in question is stationary. 2 photographs of the star are taken at a 6-month interval. The star will have moved somewhat against the background due to the shift in the Earth's position as it revolves around the Sun. Half of this observed angle, expressed in arcseconds, is used to calculate the distance to the star in parsecs. A parsec is the distance at which one astronomical unit subtends an angle of 1 arcsecond. In other words, d is equal to 1 over p, where p is the angle in arcseconds and d is the distance in parsecs. A parsec is roughly 3.26 light years. Because of this definition, it's easy to determine the distance to a star by measuring its parallax angle. Stellar parallax is subject to some error. To begin with, the star isn't stationary. Over the course of 6 months, the star's proper motion will have carried it some distance along the course of its orbit around the galactic center. Stellar distances being what they are, the differences are not material and can be corrected for by astronomers on a case-by-case basis by measuring the star's proper motion beforehand. Other factors can also add to the error, and again, astronomers can take this into account. Spectroscopic parallax is a complementary method for measuring the distance to a star. Given the apparent magnitude and spectral type of a star, the absolute magnitude can be estimated and the distance in parsecs can be derived by applying the appropriate formula. The key point is that regardless of whether Polaris is 323 or 433 light years away, it is well beyond the lower limit for optical infinity. Note also that we don't need to know exactly how far away Polaris is, or even that it's a star. All we need is for the light we call Polaris to be at optical infinity. It's just a reference point we use to establish our position on Earth. Assuming we reject the Polaris of scenario 2 that relocates itself to accommodate the latitude of anyone who happens to glance at it, how might flat Earth proponents respond? Perspective has been offered as a possible mechanism for accommodating the Polaris observation to a flat Earth. The claim is that as the observer travels away from the pole, perspective causes the light to drop in apparent altitude toward the center of the observer's line of sight. Let's look at perspective a bit more closely. This is an orthographic view of a hallway, a standard representation typically used to envision perspective. The blue circle is the observer's eye, 6 feet above the floor. The yellow circles are lights in the ceiling, 12 feet above the floor, located at 3-foot intervals. The angle at which the image of each hallway light enters the eye changes with distance. This change of angle can be predicted by the formula theta is equal to arctan of h over d, where h is the altitude of the object, d is the distance to the observer, and theta is the angle of observation. On the right is the observer's view down the hallway, with the lights placed as they would project onto the observer's field of view due to perspective. The red dots on the left place the projections from the perspective view back into the orthographic view, a frequent request from flat earthers because they think this will demonstrate how the lights would disappear behind the horizon. Instead, we see that the lights begin to level off with distance, approaching but never quite reaching eye level. The fact is that an orthographic view of this tableau does indeed include perspective. Most flat earthers insist that geographic coordinates of their flat world are equivalent to those of the real world, and that physical distances between locations are unaffected by the shape of the Earth. Claiming otherwise raises more questions than it answers, so let's go with the postulate of equivalent distances. We can therefore use 111 kilometers as the standard distance between degrees of latitude. This is rounded a bit from the actual figure, but that won't make a material difference here. This diagram shows the declination of Polaris on a flat Earth from the North Pole to the equator. By the 70th parallel, the expected declination differs from real-world observations by a material amount. By the equator, beyond which Polaris is not usually visible, perspective alone would leave the star 33 degrees higher in the sky than in the real world. The first 90 degrees of latitude account for only 57 degrees of declination. Perspective is obviously not the cause. As with the lights in the hallway, perspective effects level off with distance. From the North Pole to the equator, perspective accounts for 57 degrees of declination. Now, on a flat Earth, there's no reason you shouldn't see Polaris from the edge of the ice wall 180 degrees latitude from the North Pole, where it would still be nearly 18 degrees above the horizon to any flat earther who's managed to penetrate the cordon of laser-toting penguins in the Antarctic exclusion zone. Demonstrating the diminishing returns of perspective, these additional 90 degrees of latitude would reduce declination only by an additional 15 degrees. The star's declination reaches the human eye's average limit of visual resolution of 1 arc minute at about 22.5 million kilometers. That's nearly 14 million miles, or 58.6 times the distance to the moon. But being an intense source of light, it would never disappear below a flat Earth horizon. Another claim made against the Polaris observation involves refraction of the star's light in such a way that either the linear relationship between the declination and latitude is wrong, or that the altitude of Polaris only appears to change, or that refraction makes up the difference between the perspective declination values and the real-world observations. All three claims come to the same thing, that refraction, alone or acting with perspective, is sufficient to account for what we actually see. Refraction depends very much on local atmospheric conditions, but it's possible to calculate it for a standard set of conditions and to modify it as those conditions change. In this formula, r is the angle of refraction in arc minutes, h is the apparent altitude of the astronomical object above the horizon, p is the atmospheric pressure measured in kilopascals, and T is the temperature in degrees Celsius. An arc minute is 1/60th of a degree, or 0.01667 degrees. On the left is the range of refraction values for altitudes between 0 and 90 degrees. Note that at 1 degree altitude, refraction is a bit less than 34.5 arc minutes, or just over 0.5 degrees. On the right is the comparison of real-world and flat Earth perspective declinations, including an adjustment for refraction. Do you see the red, unadjusted flat Earth values peeking out above the blue line at the equator? That's how much difference refraction typically makes. The idea that refraction can make up the difference is an especially egregious bit of ad hocery. The required refraction would have to account for tens of degrees of change, with the change occurring at a linear rate. In fact, this does not occur. Astronomical refraction at its most distorted is measured in the single digits. If this level of refraction existed as a regular feature of the atmosphere all over the world, it would be very obvious to us in many observations, not just of Polaris, and would be noted in the literature. No one has ever witnessed the magnitude of refraction required to make this observation work on a flat Earth, much less encountered it as a standard feature of the atmosphere. In short, this excuse also fails. The third flat Earth excuse is that we don't know what Polaris is. Pretend for the moment this is true. So what? All the observation needs is a light in the sky at optical infinity that doesn't apparently move around in real time. Check, check, and check. We use Polaris because it's placed conveniently at the celestial North Pole, which works well with the established global coordinate system of latitude and longitude, but any star, including the Sun, should do the trick. This objection also fails. The fourth flat Earth excuse is that we use non-Euclidean geometry to visually perceive a Euclidean world, so our perceptions can't be trusted. Let's pretend this is a valid concern and work out the impacts. In the context of human anatomy, while the eye itself might be round, light doesn't travel along its curved surface to the retina, but rather directly through the vitreous body, so barring some organic problem with an individual's eye, the shape isn't a material impediment to measuring the position of Polaris. We can minimize the possibility of error introduced by the quirks of anatomy by measuring the declination of Polaris with an instrument like a theodolite. It's true that at some point in the process, the hands or machines that built the instrument were guided by the human eye, but any error introduced by its shape applies to all visual perception and cancels out. Or are we to believe that the eye introduces visual errors only when we look up at the sky? Our day-to-day experience of the outside world validates the images we receive through our eyes. We see a cup on a table in front of us, reach out for it, and find the cup to be where we perceived it to be. And isn't it ironic that the Flat Earth commandment to trust your senses doesn't apply when that sensory input threatens the Flat Earth narrative? Now for a bit of housekeeping and a prediction. Special thanks to Conspiracy Cats and his evil twin Baldy Cats for bringing the Polaris observation to my attention. The number of people who've heard of my channel and not cats is vanishingly small, I'm sure. But if you're that 1 in a million viewer who doesn't know him, please check out both his channels. He combines a teacher's understanding of physics with a wicked sense of humor. Now for the prediction. I've exercised this observation a bit before publishing the video to see if I could cover the most obvious and most popular objections from flat earthers. The number one critique has consistently been some cavil about the nature of Polaris, which completely misses the point that we don't care what Polaris is, or even that it moves a tiny bit from our point of view. The evidential payload of this observation is that the declinations change in such a way as to rule out any shape but a sphere. I have two postulates for why this is so. One, some flat earthers really are innumerate, and even geometric proofs with pretty pictures are beyond their level of understanding. Or two, some flat earthers know all too well what the observation means and choose to attack the nature of Polaris because they can't argue against the geometry. And thus, mathematics is the key to grasping the world. The Polaris observation is a real-world phenomenon possible only on a sphere, and which can be replicated by anyone with the means to travel to different latitudes, or by any group of people which is already distributed geographically. Like the shadow the Earth casts on the moon during a lunar eclipse, it demonstrates that it's possible for something beyond the limits of the Earth to inform us of some aspect of our world, because it represents the outcome of a fundamental geometrical relationship between the Earth at a distant reference point, and because there is no credible mechanism to replicate this observation on a flat Earth, the Polaris observation serves as a strong falsification of the flat Earth hypothesis.